Good.
So it's my pleasure to introduce Simon Portegies from Leiden. He's going to talk about the solar systems, probably. So take it away.
Thanks. Yeah, it's a tremendous pleasure to be here, and it's interesting if you go on a sabbatical and you think, where shall I go, and you decide on an institute where I've never visited before, but I knew many of the people here by name and many of the people in the neighborhood, and so it's sort of a gamble, right, to go to an institution where you don't know anybody. On the other side, if you go to an institution where you know everybody, you just immerse yourself among your friends, and you will talk to your same friends again. So it gives an opportunity to talk to people I normally won't talk to, and the other way around, and to expose you a little bit to the science that excites me. In that sense, I'm absolutely very happy to be here visiting and welcomed in this fantastic way. And the science that excited me, or at least it started like a hobby 10 years ago or so. And I was still an assistant professor in Amsterdam. And I got interested in the solar system because I was writing an article for Scientific American about star clusters. And the editor of Scientific American, he said, you know, star clusters is almost so interesting. You should say something about the sun. I said, the sun, you know, is the most boring star in the entire galaxy, because as far as I know, it's the only single star in the galaxy. And he said, yeah, but you should say something about the sun. And then I thought, well, maybe the sun is not so boring as I think it is. Maybe it was born in an interesting environment. Maybe it was born in a star cluster. So I rewrote the entire article in the sense that the sun may have been born in a star cluster. And George Musser, who was the editor, was very happy with it, published it. And this is how the solar sibling story starts for me. And it was also the time I got the offer I couldn't refuse from Leiden. And the director there, Tim, was just becoming the director general of ESO. And Koen Kuijken was just the new director of Leiden. And the day after Tim left Leiden, basically, Koen invited me, like, you know, we should have you as a professor here. And I told him about the solar system story, and he says, well, maybe we should forget about that part. That is, you know, really too speculative and not really that interesting. But so it has a second story, the solar siblings, and I just wrote a new paper on it, which will be out next week or something, and I will tell you a few things about that. Well, it's under review, but the reviewer is friendly and positive. So I don't expect it to have big troubles anymore. But it's recorded, so I hope he doesn't see this. So it all starts with this artist impression. This is actually an artist impression of Setna, and I will not talk about Setna, which is an extremely interesting object in the solar system, I think. But it's just to amaze me about how artist impressions, how journalists look at astrophysics, right? So this is Setna, and this is the sun in that case. So Setna is being, you know, illuminated by the sun, but I think there is a second star somewhere on this side, right? No idea which star that should be for all the luminosity here, the reflection over there. And then what is this planet? Which would be very interesting. Maybe that's planet 9 or planet 10 or whatever you want to call it. I think here in close to the United States, it's planet 10, right? And in Europe, it will be planet 9 in that case. But this is a sort of an outside view of the solar system. But if you look at the solar system and how this story started, it's really with an asteroid. And this asteroid hit the Earth. It's the Allende asteroid. It hit Mexico. There was a newspaper article about it in 1969, and saying there was a big flash from the sky and it penetrated into the ground. And people started looking for it. In this part of Mexico, in the little town of Allende, it was found. It was a little piece of rock, which is now in a museum in the United States. And it turned out to be a very interesting piece of rock, because when they cut it open, they looked into the little chondrules and into the little calcium aluminum inclusions in that rock. They found, first of all, the age of the solar system. And the age of the solar system is being measured in lead and in uranium-corrected lead age determination. And if you go to a geological conference, they quibble, the geologists quibble about, you know, if the Earth is 10 years younger or 10 years older than what the previous speaker has been talking about. So the age of the solar system is something like, we say, 1.5 or 1.6 billion years. But the geologists go to many more decimal places. And well, maybe not on 10 years, maybe in 1,000 years or 100 years. And this is basically the evidence for it. This is the peak in the age determination of the sun and the lead measurements of the age of the sun. But there is more interesting stuff in these aluminum, calcium aluminum inclusions and in the chondrites, which is the overabundance of aluminum. 26 aluminum is an interesting element. And in 2006, Looney wrote this article saying, okay, the way to explain this overabundance of aluminum in the Leiden meteorite would be by producing it in a supernova. The supernova will produce all these heavy elements. 26 aluminum is radioactive and it has a decay time of about 1 million years. And what they find is these decay products in these matrix structure, in the crystal structure in the asteroid. I didn't understand this at first, and I wrote the papers about it. So I went to a geologist and he explained it to me, and I still didn't understand it. So I went to a chemist and I asked him, how can you recognize that element in these asteroids? And he explained it to me, and I didn't understand it. And then I went to an astronomer and I asked him the same question, and he explained it, and he says, well, it's very easy, right? It's just in a matrix where, in a lattice structure where this, the aluminum is being encapsulated, and when it decays, this funny product will stay in the lattice. So you see the decay products of the aluminum in the lattice where it doesn't belong. And chemically it doesn't belong there, so the only way to get it there is that the aluminum is encapsulated into the crystalline structure. So I understood it, and then I wondered, why didn't I understand it when the chemists were telling it me or where the geologist was telling it me? And I think it's just the language barrier between the astronomers and the geologists and the chemists. But anyway, they argued that at a distance of within 1.6 parsec, there must have been a supernova producing this aluminum. And it is produced by a star of between about 20 solar masses. And if you consider that the current most massive star is Spica at about 100 parsec, in the early days, stars of this mass must have been very close to the sun, within about 1.6 parsec. And the way to do that is, of course, to put the sun in a star cluster. In the star cluster, a star explodes, produces all the aluminum, puts it in the interstellar medium. If the sun still has a disk, it is rained onto the disk, and in this way, it could be embedded into something like the Leiden asteroid. So what you can derive from that, sort of, is how many stars? The question that remains then is how big would this cluster be? Now, a very rough estimate would be if you need a 20 solar mass star, these are rare, so you need about 1,000 stars before you get a 20 solar mass star. So the cluster would be about 1,000 solar masses or so, or 1,000 stars. What would be the size of the cluster? Apparently something like 1.6 parsec, because that was the distance needed in order to pollute or enrich the solar system. You can wonder where in the galaxy was this star cluster formed, but probably somewhere on the orbit. If you would calculate it backwards, if you can. And where are the other stars now, and can we find them back? So where are the solar siblings, in some sense? And then you can start thinking about baby picture of the early solar system. Was the solar system born in an environment like Orion? Was it born in one of these star clusters in the LMC, like the low mass or the young low mass star clusters? Or was it born in one of those massive, young, dense star clusters like R136, as you see here? And that, of course, would be an interesting question, in particular also if you want to know what for influence does it have for the further evolution of the solar system, and is it possible to find any of the other stars that were part of that same cluster back with, for example, Gaia or so. Now, this talk is mostly from a numerical perspective and a little bit from the idea of the solar system, the birth of the solar system. And the numerical stuff is done, what we talk about mostly is done with AMUs. And I have the t-shirt of AMUs. I can say, I'll show you the back, t-shirt AMUs. That's the code we have been developing for the last decade or so. And it's not a code. I call it a code now, but it's not really a code. It's a piece of software. It's an environment. It's an environment in which you can like a laboratory in your computer. You can take codes and put them together and combine the answers of different pieces of software written by maybe people in my group, but maybe other people who have written codes over the last decades. So it's built on public codes, and there will be an article in Science today which talks about dinosaurs. And dinosaurs is a code that has been written, a sort of legacy code over the last 30 or 40 years, without any structure, which is very common in astronomy. And don't take it as a very negative thing. Dinosaurs is not necessarily negative, because dinosaurs, these are the chickens of today, right? So it's just the garden variety type of codes people are using. Now, in AMUs, we use at least 2 solvers for each type of physics. And the types of physics is gravitational dynamics, let's say embodied dynamics, hydrodynamics, in the flavors of grid-based hydro, AMR, or SPH, radiative transfer, different types of radiative transfer, and Monte Carlo type of radiative transfer, or the ray tracing radiative transfer codes, and stellar evolution. And there are also different types of stellar evolution codes. The interfaces to all these codes are standardized. So you can write a script. Basically, we use Python to do that. And you can write a script. And if you call a certain code, and you say, oh, I'm not really happy with that code, you throw it out, you change this one line of the script, and you call a different code, and you get the same script itself, except for this one line, but it will do something completely different. Right? So you have to be careful about that one line. But if you want to change, for example, from one embodied code, let's say a 4th order Hermite predictor corrector scheme that runs on a GPU, to a tree code that runs on a Beowulf cluster, then you just change one line of your code. Many of the codes are parallel, GPU, grids, clouds, high performance, whatever. They're written in the original language. So they're codes written in Fortran, in C++, in Haskell, in Ruby, in CUDA, in assembler, all under the hood. And they're all combined in scripts. And the script language we use is Python. So with Python, you call the codes. Under the hood is a high performance engine. But the calling sequence is in Python. So I can work in an easy environment, the Python environment, but when I call the code to really does the work, it is sufficiently high performance to not seeing the bottleneck of the Python being a slow language. And a few things that we added was like unit conversion. One code can be written in dimensionless n-body units, for example. And in stellar evolution codes, people like dyne per square thumb, for example, as a pressure unit. But in the environment itself, we convert everything to CGS and SI, whatever you need, or solar masses per cubic parsec or something, whatever you want to use. So you're flexible in that. Then we have advanced code couplings in it, which means that we can combine the output of different codes together at runtime and make them into a self-consistent solution with a hybrid solver. So if you combine the hydrodynamical results and gravitational n-body results, you can combine them into a self-consistent gravity hydro solution. And that is a technique we call bridge, and it is based on basically a Verlet integrator from one code to the other code. And I can give an entire different talk on that. It would be interesting, but it would be very technical. And the intention here was not to be technical. There are more than 400 example scripts. So there are many scripts. You can just take a script which does something very similar to what you're interested in and then change it to whatever you need. And it is free. It's on GitHub. And we have a web page. And you can download it and use it if you like. And to give an example of a few codes which are in there, you may recognize a few of the names. These are direct and tree-based and symplectic n-body codes. Stellar evolution solvers, including binary evolution solvers, hydrodynamical codes of different flavors, and radiative transfer codes. And in total, there are like 50 or 60 codes which are under the hood of this framework. And the nice thing is, and one of the reasons to have a sabbatical at all, is that Steve McMillan, my co-author and friend and collaborator for a very long time, written a textbook on this framework, how to do it, how to use it, and how to apply it for student projects, for example, have master students, PhD students, maybe postdocs work with the environment and have fun and do science with it. Now, having introduced the code, actually I have not introduced any code. I really have introduced sort of a framework in which we use to do the calculations. Let's go back to the burst cluster of the sun. Let's take a star cluster of 1,000 stars and just let it go in a computer and see what happens. Just as an experiment. So we do an experiment. We take 1,000 stars. We put them in sort of a fractal type of initial realization. We solve the gravity. At the same time, we solve the stellar evolution. And you see the colors change. To make it a little bit more interesting, we overlay the Hubble Space Telescope point spread function. And Inti Pellepessi, one of the co-authors of Amuse and collaborators, have been making this movie. And we just run it. And what we do, we just measure what is the typical distance between a solar type star in this simulation and the supernova. And the supernova are very easy to recognize. These are these, if they change in color and they blow up, then they disappear. And if they don't disappear, but a very small object appears, you see this is a binary, for example, and the companion is continuing in its orbit when the supernova is exploding. This is a 1,000 particle system with a 1 parsec virial radius, and the relaxation time of such a system is typically a few million years, a few tens of millions of years. So you see it dissolves also on the time scale. Well, the time scale is not here displayed, but you can see the stars evolve. So the first star to go bang is probably like a 20 solar mass star. So typically in this system, so it will be like 7 or 10 million years or so when the first supernova goes off. And now it dissolves in the tidal field of the galaxy. So this whole simulation is done in the tidal field of a galaxy, which is analytic potential underlying basically the solution for the gravitational interactions.
And is the evolution mainly by evaporation of low mass stars, or
the evolution of the system?
I mean, the dissipation of the system, the tidal field of the galaxy, is mainly by evaporation of lower mass stars?
No, the most important part actually is the mass loss in the massive stars and the relaxation. So this cluster is sufficiently young that self-relaxation is important. And the mass loss in the early supernova and windy stars can be up to about 20% of the mass of the cluster in the first 30 million years or so. So on this time scale, the cluster has lost a considerable fraction of its mass just by stellar evolution already. That causes it to expand, and then the tidal field starts eating up the outer parts, and the tidal radius shrinks into the cluster. Yeah?
So it's mass segregation an important part of the story?
Yeah. Yeah, mass segregation will happen here, and you see it basically happen if you look closely. The massive stars.
Then they disappear.
Yeah, they disappear quite the moment you spot them, because they become orange. They're already in the center, and then they disappear. Yeah, yeah. Well, I can show you many more of these simulations, or give an entire talk on these simulations, but this is not the point now. So let me not go too much into the dynamical evolution of these clusters, but more go into, let's say, the consequences for the solar system. So if you have a star like the sun and the planets, or maybe a planetary disk in such an environment, what would be the consequences of these exploding stars on the solar system? Now the easiest thing to do is just measure the typical distance between a sun-type star, let's say a star of 1 solar mass, plus or minus a little bit, and a supernova. And you see we had many supernovas in this simulation. There was about 15 or so. And if you count the first 9 supernova, what is the typical distance? And here's a cumulative distribution of that distance as a function of the supernova. So the first supernova is at the typical distance of, let's say, about a parsec. And the 9th supernova is a typical distance of about 10 parsec. So in this time scale, what you basically see here is that the cluster is expanding in a time scale of, not in time, but in time scale of the number of supernovas, so to say. And what we're interested in, of course, is what is the probability that the sun really gets sufficiently close to a supernova to either enrich the solar system, the protoplanetary disk, or do something else. Now, and how that looks like for an artist impression is an exploding star. This was an artist impression of a superluminal supernova. And this planet was completely unrelated to it, but the artist put in the planet because it's roasted by the supernova, was more interesting. But what I'm interested in, you have a star that has either a wind or a supernova. The consequence of a supernova is first a flash of light, right? That's just the explosion. And then the nuclear blast wave, the material of the outer layers of the star, will steamroll into something like a planetary system or an early solar system with a disk, a star with a little disk around it. And then you have the orientation of the disk, which is important on the effect of the supernova and the interaction with the disk. And you have the distance to the supernova. And there are a few other parameters, like how much mass is in the ejecta, what is the velocity of the ejecta, what is the temperature of the ejecta, and what is the mass of the progenitor, for example. Now, if you look at the planetary system or the protoplanetary disk, it may look like this. In the computer, it looks like this. So this is a hydro solution for a star, which is in the middle, and then a disk of, in this case, 100 AU. And this is Faison, and this is CITA. And in this case, I chose a relatively thick disk to mimic a protoplanetary disk around the star. And 100 AU is just taken because I have 10 fingers, and you square that, you get something like 100 AU. Now, the first thing that happens is after the supernova goes off, you have this light flash that radiates the disk. And I thought, well, if you can radiate the disk to a temperature of about 1500 Kelvin, then basically everything melts. So all the dust grains in your disk will become little molten droplets. And once they're molten droplets and you put in the aluminum, they can be embedded into the crystalline structure the moment these droplets will cool down. Sounds nice, right? That doesn't work. The reason is that the cooling is way too fast, but it is a nice effect. So if you have time in days, in this case, and the supernova goes off, so the blue line is a supernova, this is the light curve of a supernova in log and solar luminosities. And here I take 2 supernovae, and I didn't forget the names, but they're really not important. They are just ordinary type 2 supernovae in this case. And what you see here in the red lines is the temperature of the disk measured with a hydro-radiative transfer code. So you have a supernova at a certain distance under a certain angle from your exploding star. Now the supernova, and you have the disk with the star. And you see there is a delay time of a few hundred days, or depending on the distance. It's just the light travel time from the supernova explosion to the star. And the temperature you can reach in these disks is easily 1500 Kelvin. Right? You can go to higher temperatures if you're sufficiently close, or if the supernova is sufficiently massive. So you can radiate the disk to a very high temperature, but it cools down very quickly. Actually, it cools down again on a time scale of 3 Kelvin per hour, 0.3 Kelvin per hour. So by the time the nuclear blast wave comes in, which is way later, it's 20 years later or 30 years later, the disk is just cool again. So the droplets have already condensed into their droplet phase. So it's not a way to, so there's no time to wait. The disk is not waiting for the aluminum to come in. And if you look face on, for example, on such a disk which is illuminated from the side, you see that part of the disk is sort of heated on this side, and on the other side it stays a little bit cooler. Now if you do sort of parameter search of this calculation, you can vary, for example, the distance to the supernova in parsec, between a tenth of a parsec and 0.6 parsec in this case. And you can change the angle from the symmetry axis of the disk alongside until you're on the side of the disk. So 0 degrees here is, think about it. What? It's face on from the supernova. Yeah, exactly. So that's 0. That's face on for the supernova, and this is on the side. So if the supernova is on the edge on the disk. And what you see here is sort of the typical temperature reached in the disk. So if you want to reach 1500 Kelvin, you want to be below something like 0.4 parsec, and the angle depending on sort of what it is here. Now that's very nice. So you can sort of roast the disk by the supernova. But the blast wave is has a much bigger impact on the disk itself. And first of all, what the blast wave is doing is a relatively straightforward hydrodynamical calculation. You take a disk around a star and you blow in a supernova blast wave and you just look what happens. And this is basically what happens. This is the work from Thomas Wijnen. Thomas was a graduate student doing these calculations, and he wanted to put in actually a protoplanetary disk in the wind of a star in a cluster. But we also did the calculations for the supernova. The first thing you do is you blow away the outer parts of the disk where the density gets a little bit lower. And then you're loading the disk with 0 angular momentum particles, or low angular momentum particles. So the disk is also shrinking as a result of accreting from the wind of the supernova blast wave.
So in this case, the final radius of the disk would be comparable to the body radius for that velocity.
Yeah, and a little bit smaller than that, actually, because also of the 0 angular momentum loading. Yeah. So you can measure the disk profile. If this is the initial disk profile in a particular simulation, and after you perform the simulation, you drop the density profile on the outside, but the inside is basically not affected that much. So there is a certain radius below which you're affected or where you're not affected. And here in the dark blue line is basically the density profile of the current solar disk. So if you take all the planets and all the planetesimals and smear them out over a ring, and you add them up, then this is the blue line is sort of the density profile of the projected density profile of the current solar system. And the thing that I found very striking on this picture is 2 things actually. It's this enormous drop-off after 45 or so AU, the Kuiper cliff. as we call it. And actually the peak there is also interesting, which is the scattered, mostly the scattered Kuiper belt objects. And the other thing that's interesting is this enormous trough of things where there are a few peaks, which of course are the massive planets and their Trojans and objects in their asteroid belts. So if you say that the solar system is cut off at about, let's say, between 40 and 50 AU or so, we are looking for a planetary system that is born in a star cluster and for which a nearby supernova or another process, like encounters with other stars, has cut off the protoplanetary disk to about 40 or 50 AU. That's what we're looking for, right? And you can do the calculation by looking into the calculation, doing the same grid of calculations again as a function of distance to the supernova and the angle, as we discussed before, the incident angle, as I call it. And you see that you need to be in a range of this sort of funny greenish color. So if you're very much face on the disk, you can be farther away and still affect the disk very dramatically. And if you're edge on, you have to be a bit closer and in order to really destroy the disk. And this disk is more resilient against perturbations from a supernova nearby. So now what we can do is overplot this sort of regime into this temperature plot, which will look like this. So this is the regime, and this is so that's the shaded part, and this is the regime. The purple part is the regime where you have a sufficiently high temperature in order to melt the dust grains in the disk. So you could say that this part here is the part in which I'm interested in order to make what you call a solar system equivalent type of environment. Yeah.
Isn't another criteria is that the column density of the supernova ejecta equals to the column density of the disk, or something of that sort?
Yeah, so that is there are several effects which play a role. So it's the baryon loading basically, right? You push away the material, and it is how gravitationally bound is it, and how much do you heat the disk also at the same time. So there are several processes operating in the same time, evaporating the disk.
So when you say 40 AU, which dominates, determining what effect dominates determining the outer edge of 40 AU?
So it's a combination of effects of the ram pressure. It's mostly the ram pressure of the supernova ejecta onto the disk. So really.
Another way of asking the question is the mass removal momentum or energy removal?
It's both, right? So the energy pressure is the first sort of impulsive effect, and the momentum effect is the shrinking of the disk due to the accretion of zero angular momentum material.
And to what extent is radiative cooling limiting mass loss from the other disk?
I don't think that radiative cooling is very important in this case. It's mostly these two effects which sort of compete for shrinking the disk.
The impact speed is high, so the temperature reverse shock is very high.
Yeah. Yeah. I'll come back to that actually, to the temperature in the shock. Yeah. Because it's important for.
You're saying there's a shock heating of the remaining disk.
Yeah.
That's significant.
Yeah. So there's another effect which you could see in the movie, which I just showed. So I'll show the movie again. And that is if you have the blast wave hitting the disk. This disk was at an angle of 45 degrees with respect to the incoming accretion stream. But what you also see is that the disk is sort of tilting. So the interaction of the blast wave material with the disk causes the disk to change its orientation. And JJ just gave a talk about this. And this is another way to sort of tilt the disk with respect to the rotation axis of the star. And if you look at the solar system, this also happened in the solar system itself. So the angle between the ecliptic plane and the equatorial plane of the sun is about 6 or 7 degrees. And the question, of course, is could this process be responsible for doing this in the solar system? So you can parameterize this effect once you have understood how it works.
Can you come back to the previous one? So if I understand at this point, you're considering a case where the supernova happened before there were planets in the disk. But in principle, if you had planets, then they wouldn't be affected by the shock wave, right? They would just be too small.
Yeah.
So this could be.
Yeah, you want this happening before the planets. Yeah. Except if the disk is so massive that the disk tilts, then the planets are sort of carried into the plane of the disk again.
Yeah, but then it would be a less efficient effect, and then you would
Yeah.
have to transfer angular momentum from through the disk. from the wind to the disk and from the disk to
Exactly, exactly. So ideally you do this before you have any planets. Now this effect of tilting the disk, you can parameterize that in this function, where the inclination driven by the supernova blast wave is a function of the mass of the blast wave, the distance, and the incident angle, and it's most effective at 45 degrees angle between the supernova and the things, and least effective at a face-on, and no effective face-on, or if it's on the side. Right? If it's on the side and you blast, you don't tilt the disk, and if it's face-on, you don't tilt the disk either. Now you can overplot again this diagram or the measurements of that with the temperature of the disk due to the irradiation of the supernova, and that is sort of this V-shaped sided, the greater than shaped thing as a function of distance and incident angle. And in order to get it into the sufficiently hot regime, you're again in this regime. Now you can overplot the cutting of the disk, the truncation of the disk at about 40 or so 50 AU, and the fact that you want the angle confined to about 4 or 7, between 4 and 7 degrees, as is observed in the solar system. You overlay the two, and you get the criterion for cutting the disk and the criterion for tilting the disk. And in the hashed region is where you have both confined. So there is a regime where you can say, hey, if the supernova is at a certain distance, let's say between 0.4 and 0.2 parsec, and at an angle between 30 and 60 degrees or so, you could tilt the disk and cut the disk away, as we see in the solar system. And if you, for one of these simulations, look at sort of the evolution of the tilt of the disk, this is the initial disk. The red points are the planets in the solar system. The green is after 100 days, and the yellow is after the impact of the supernova shell. So, I mean, I don't know if you believe that the yellow curve follows the red or the red follows the yellow, but it is not completely different, at least not on this scale. Now,
Just one more question, but how do you solve the problem? So you have in principle some freedom as to how to choose the thickness, the radial thickness of the shell as measured from the point of the explosion. Like, I mean, you have a set-off like blast moving into.
It's also.
Yeah. I disagree with you. Okay. If you have a set-off like blast, you get a certain thickness. If you have a radiative shell, you get another thickness. If you have a freely expanding stellar shell, which probably isn't relevant in this context, you get another thickness.
yeah.
So the question I have is simply, which of these you get depends on what the gas and the residual molecular gas in the star cluster might be doing. You know, I mean, you're forming the sun, so presumably there's still some molecular gas hanging around.
Yeah.
So the question is simply, to what extent is the end result of the interaction converge with respect to your choice of not only the column of the material, but the radial thickness of the material? Or does it depend on that side?
The first answer is I don't know. So the shape of the radial shape of the supernova shell, what I took was a very, very sharp edge and then sort of a power law decay. And how that changes the result of this, I don't know, because I didn't try. So it would be a matter of experimentation to see if you take a very thin, massive shell or a more smoother slope, what sort of effect would it have? That would be interesting to do, but this is just a sort of first order estimate for this process. So the thing where we started with is, can you get enough aluminum from the supernova shell? Can you accrete enough material from the supernova shell onto the disk? And that is very easy to measure now, because you just, you look in your calculation and you look, this is the mass of my disk and this is the mass of the accreted material. And you can make, again, a plot of distance versus incident angle. This is our hashed region where we think we're happy with that regime of distance and incident angle to explain the size of the disk and the inclination of the disk. And it turns out that in that regime, you accrete something like 10 to the minus 7 or 10 to the minus 6 or 10 to the minus 8 is a relative fraction of the disk, which is way smaller than the 10 to the minus 3 observed. So you cannot accrete enough material, aluminum in particular, onto the disk. So the supernova cannot have been responsible for loading the protoplanetary disk with aluminum. And another thing you can look at is So the other thing which is important, which I started with actually, is the temperature of the disk. So the supernova blast wave will also heat up the disk in the shock. And that is actually quite promising, because the temperatures of the disk in the same parameter space, you heat about half the disk to a temperature of higher than 1500 Kelvin of the surviving disk. So the disk you can make hot enough to melt the disk for the second time in this case. So first time was in the radiation of the supernova. The second time was in the blast wave of the supernova. So you can melt the disk sufficient, but you cannot get enough aluminum into the disk.
Unless it's really close.
Unless what?
Unless it's really close.
Well, if the explosion is really close, you destroy the disk. So there is nothing left. And if the explosion is too far away, you don't truncate the disk. So there is really a detailed balance between, can you do this? You can't get enough material into the disk with surviving it. Yeah? So in order to make chondrules, you need about 1500 Kelvin. So that is enough to melt corundrum and other massive tough elements and make them into droplets.
Can I just ask, how are you deciding what temperature the disk is reaching in this scenario? So you have the supernova shock come through. There's a sort of non-radiative solution for the post-shock temperature. And how are you solving for the radiative evolution of the disk material? Is this using the amused framework?
Yeah. So this is using a combination of hydro. This is an SPH code we used here, and a radiative transfer to get the radiation properly propagated into the hydro.
Is it dust dominated?
We did calculations with dust, including the dust, but it makes a 10% difference or so. It's not so even if the disk is dust dominated, it's still not affecting the results very much.
So the other thing I want to ask is, suppose you do mix it with some molecular gas in the cloud, which is not dispersed yet, and you slow down the supernova wind. Would that cause much higher aluminum accretion pressure?
I'll get to that in a sort of different direction than you may think of. And that is that the supernova can truncate the disk, in principle. It can tilt the disk to the required angle, but it cannot load the disk with enough mass. But before the supernova, you may have another phase of the star. If it's, for example, a sufficiently massive star, like a Wolf-Rayet star, which has a much slower wind than the supernova blast wave, and is also rich in aluminum. So can we maybe first have the Wolf-Rayet wind and accrete the disk from the Wolf-Rayet wind, and then have the supernova truncate the disk and tilt the disk and heat it, and then keep the accreted aluminum from the supernova, from the Wolf-Rayet wind into the disk. But of course, then you have to take into account that the aluminum is decaying while you have to wait for the supernova to go off and heat the disk in order to get it into the crystalline structure. So you have to make the code a little bit more elaborate to do this. And now you don't want to do it in a grid of like you do here. But now I take just a star cluster. I solve for the equation of motion of all the stars. Each star gets a disk. I take into account when a star becomes a Wolf-Rayet star, liberate the gas from the Wolf-Rayet star, gets it into the interstellar medium, let it accrete onto the disks of the star, and by the time a supernova call is happening, I look at the individual disks, see what the effect is of the supernova on that disk, truncate it, tilt it if necessary, heat it, preserve the aluminum if it's there, and then continue this whole process until the second Wolf-Rayet star supernova happens. And I give you one example, well actually 3 examples of how that looks like for 3 stars. There is a blue star, a green star, and an orange star. And the vertical, so this is time, and I go up to the age of 40 million years, and that is the time when the last supernova basically goes off. The vertical lines are the different supernova, and the thickness of the line gives you the amount of mass in the supernova shell. So the massive supernovas happen in the beginning of time, and the thinner lines when there is little mass in the supernova shells at the end. And the top line gives you the size of the disk, so how is the disk truncated. The middle line panel gives you the aluminum loading, and the bottom line gives you the inclination change of the planetary system.
What's the rough timescale of those jumps?
I'll get to that. depends on the process. So what happens here is that before supernovae happens, the disk of this blue star is being truncated by passages with other stars. So these are impulsive encounters with other stars in the star cluster. If another star passes by, the disks of that star is being truncated by mass being unbound from the star in the interaction with the other star. And then when the first supernova happened, the disk is already so small, or the supernova is so far away that the supernova basically has no influence on that disk anymore, and it remains in the same size.
There's no viscous spreading.
In this calculation, no viscous spreading. Yeah, that's correct. So in the later calculation, we do viscous spreading, but that is still in preparation. Then they grow back. And then indeed the supernova may be affecting the disk again. In the aluminum, for the blue star, you see that it rises from 0 to basically a certain value by the winds of the Wolf-Rayet star. So the disk is accreting from the Wolf-Rayet wind, but it's not accreting very dramatically because the disk was already truncated by the time the Wolf-Rayet star started blowing its wind. And then the supernova happens, and the material is preserved in the disk. So the amount of aluminum is frozen into the crystalline structure of the disk. But not completely. You see here the decay of the aluminum. So these supernovae were insufficiently nearby to really melt the disk, to get the disk to a temperature of 1500 Kelvin. And it's only this supernova at an age of about 50 million years that preserves the disk. So the aluminum decays, and then it preserves. And the inclination is sort of a random walk in time. If you look at the green star, which is not affected by dynamical encounters, it is basically truncated by the first supernova that happens in the calculation, in this case. And you see that it sort of accretes material quite heavy from the Wolf-Rayet star. So this star was nearby, but also the disk was still big, so it could also have a big cross-section for accreting the material. And that supernova immediately fries this disk so that the amount of aluminum is frozen into the crystalline structure, and therefore it doesn't change anymore. And the orange star is again is not affected by any of the supernova here until it is being truncated by two supernova in short succession, but not by dynamics. So that was a star probably more on the outside of the cluster. Maybe it sunk to the more inner part where the supernova happened, and then it was preserved. And you see that also in the decay of the aluminum, right? It's accreting from a Wolf-Rayet wind, but then it sort of decays until the supernova that truncates the disks, enriches the disk a little bit, and that material. So this is an interesting peak. The material that is being injected into the disk cannot have been fried by that same supernova, but you need the next supernova to fry the disk because it's the radiation that preserves the aluminum into the disk and not the supernova blast wave, because that's too late. So this is the typical evolution of three systems. And the interesting part of the blue line is that dynamical encounters also are important, apparently, for truncating disks. So you can see that here, that the typical, as a function of time, the typical size of a protoplanetary disk around a sun-like star decays from 400 AU in this case to a size of about 50 AU. And the blue line gives you the number of supernovae that happen. So the first supernova happens at an age of about 6 or 7 million years. So the first 7 million years, it's the dynamical encounters that truncates the disk, and the supernova can only be effective at later time. Yeah?
Do you take into account viscosity into this?
No. No, so these disks are not viscously evolving. No. Now, if you do this for a whole grid of calculations, is let's say the number of stars in a cluster versus the size of the cluster, and you modulate that by the Schechter function, what is the mass function of star clusters born in the galaxy, and what is the size distribution of star clusters born in the galaxy, and you add it all up, and you count the number of star clusters that produce solar-like stars, so solar equivalent stars. And a solar equivalent star is a star that has a disk that is truncated between 40 and 50 AU, that is tilted with respect to the rotation to the original inclination, and that is sufficiently enriched as the solar system. Then the most likely star cluster in which a sun-like star forms is at a size of about 0.7 parsec, and about 2,500 stars. So that's the typical. So the massive clusters don't do it; they are too violent, and it's skewed to low mass clusters. And the amount of iron you then get in your solar system. So the amount of iron in the solar system is lower than the amount of aluminum by about a factor 1,000. It's a large range, but it's reasonably in the ballpark. So this is the amount of iron. 60 iron, it's also a decaying product like aluminum, versus the amount of aluminum, and you sort of match the observations. But I have to say that basically everything would fit in here, right? I mean, it's like many orders of magnitude on both axes. So the arguments of enrichment in favor by a Wolf-Rayet star followed by a supernova is the evidence of multiple heating in the chondrules, the outer edge of the Kuiper belt, the presence of the Kuiper cliff, being truncated either by dynamics or by a supernova, but I'm not sure what is most important. The tilt of the ecliptic with respect to the equatorial plane of the sun, the presence of 26 aluminum in particular the Allende meteorite, and at the same time the lack of iron 50, which I didn't really discuss that much. So the last question is, where are now all these stars, right, in this cluster? So you do this calculation in the galactic potential, and if you take a sort of a zooming view of the top, so the galactic potential here is an analytic potential with 4 spiral arms, and the reason I take here 4 spiral arms, it looks a little bit, it does more damage to the cluster, so to say. And these are the stars in the cluster. In this case, it's 1,000 stars. And this is how they evolve in a certain rotational frame, and how they spread out over the galaxy itself. And this is in time. And this was the work of Carmen Barbosa, one of my grad students who did this. So they're bouncing around in the galaxy. And if the sun is one of these stars at an age of 4.5 billion years, all the stars have basically spread out over the galaxy, but confined in sort of a ring around the solar distance. And of course, this is a nice thing to redo with a full simulation of the galaxy on the background, including star clusters and gas, and not with an analytic potential. So they spread out, and the question is there a star in the neighborhood which you could identify as a solar sibling? And if you go to the Gaia database or Hipparcos, as we did, and you look for a star with in this parameter space range in the neighborhood of the sun, the best candidate seems to be HD 28676, is this star. It's an F5 star, it has the right age, it has sort of the right mass, it has sort of the right metallicity, it has sort of the right proper motion, and reasonably close to the sun, that if there is a solar sibling in the neighborhood, then this would be a good candidate. And you can see it on the sky tonight. I don't know, can you see it tonight? Can you see Aldebaran tonight? But you need a little binocular to see it. It's a 7th magnitude. So I think this is the best candidate we have at the moment for a solar sibling.
How many would you expect to have within 100 whatever parsec?
It depends a bit on the evolution of the galaxy over the last 4.5 billion years, which is tricky. But in a distance of a kiloparsec, I would expect about 100. Between 10 and 100.
What fraction of stars are being formed in the galaxy in such clusters?
A considerable fraction. So if it depends on the cluster mass function, of course. And the cluster mass function is a big discussion on it. What's the shape of the cluster mass function? But if it is the Schechter shape, so that's a power law with sort of a cutoff at the high mass end, and it extends to low mass stars or to low mass clusters. And then the question becomes, what is the lowest mass cluster you can get? And then the integrand of that function. So I think if you take this as sort of an indication of in what sort of cluster could the sun have been born, I think that 2,500, 2,000, 3,000 stars, 0.7, let's say 1 parsec in diameter or in radius. Such an environment will produce something like between 10 and 20 supernovae. So the notion that the sun may have had 1 supernova in the neighborhood, it may have had 10, right? It may have been fried many times over the past, within a very short distance. But the one that really tilts the disk and can cut off the disk at the right size and push it into the right angle would be at a distance of about 0.1 to 0.4 parsec at an angle of about 35 to 65 degrees. I think that the Wolf-Rayet star is necessary to sort of produce the aluminum and some of the iron, or aluminum for the Wolf-Rayet star and the iron by the supernova, and that explains the discrepancy between the amount of aluminum and the amount of iron in the solar system. And eventually this cluster will be torn apart by the tidal field and spread over the galaxy.
So the photoscience is strong wind. Does the Wolf-Rayet wind get
Yes.
into the disk?
Yeah.
How close does it get? If you just do a momentum balance between the T-Tauri wind and the Wolf-Rayet wind, how close does the Wolf-Rayet wind get to the photoscience?
You mean in terms of the winds colliding together?
Yeah.
Yeah, that's a good point. So I think, so by the time this happens, the sun is not really, is let's say 5 million or 6 million years old. So
the differential age rate in the conjugables and the CAIs is less than that.
yeah. But when do you make the chondrules and when do you make the CI exactly?
Isn't the aluminum 26 in the CAIs?
Sorry?
Isn't the aluminum 26 in the CAIs?
Yes. Yes.
Okay, so you need to presumably then have the Wolf-Rayet wind present at the initiation of the protosolar.
Yeah.
I mean, it's there. It's the birth environment.
It's the birth environment. Yeah. Well, that may be another solution. Yeah. So that the Wolf-Rayet, you mean the Wolf-Rayet wind, what pollutes the molecular cloud in which everything is formed.
Something you must have thought of. Is
Yeah.
whether you get some sort of induced star formation.
That's right.
This big external impulse that you've actually triggered a collapse, right, or a fragmentation process, but with all this energy input from massive stars.
Yeah.
I mean, people study that in the context of massive stars.
Chondral formation and massive star formation, and yeah, exactly.
So the star is not totally decoupled from the disk. They can communicate. Do you worry about any real end?
No, I don't worry about that. But I would worry about that. Yeah. So that would be the next, like the shape of the expansion shell of a supernova, I think is important. There are many aspects. This is sort of a big overview of let's say, try to find a place. How can you explain a number of these phenomena at the same time? But I think refinement of this sort is absolutely a next step.
Well, you're never going to predict the distribution of molecular gas that's left over from the sun's formation around the sun.
No, I don't know what to do with that. Yeah,
So there's always going to be some error bar in
that's right. Yeah.
So I'm curious about solar sibling research. How many chemical elements do you look for, and what do they decide? When do they decide? When do you decide when it's a sibling, when it's not?
Yeah, I think this is very tricky. So I spoke to several people from the LOD group and other spectroscopic searches they do for nearby star clusters. And I'm not an expert on this, but they tell me that the cluster-to-cluster variation is larger than the star-to-star variation. The star-to-star variation within one cluster is larger than the average variation of cluster-to-cluster. So that would mean that searching for a star with the same chemical composition as the sun is a hopeless endeavor, because it doesn't tell you that it came from the same molecular cloud. So it would be fun to talk to these people. Yeah. Yeah.
Well, how many F5 stars like this one are there within the same volume that you reject? How rare is this?
Yeah, we don't take of course, the mass of the star is important, right? The fact that it is an F5 star, but it's mostly the kinematic of the star which is important. You want it to co-move with the sun, basically. You want to have the same kinematic characteristics, and that's where we selected the star on, and not necessarily on the chemical composition.
But the co-moving meaning all the peculiar motions around the galaxies, I would say.
Yeah.
But presumably that has been heated up around spiral arms and so on.
Yeah. Yeah. Also.
How does viscous spreading affect this truncation?
The viscous spreading in the disk, you mean? Yeah, we are looking into that. So if the disk would spread again, it would grow back to sort of a larger size on a certain time scale. And if then a supernova comes by or a Wolf-Rayet star, you can pollute it again. And the whole problem becomes a little bit less linear, so to say. So it gets more complicated, and we would have to do all the calculations, I think, to see if it really changes the picture.
Well, we don't know if there's any viscosity in this. So that's why it's
So we don't know the viscosity of the disk, or we don't know?
We don't know that.
Yeah. So that depends on the viscosity of the disk. Well, can of worms. Yeah.
I wanted to ask about the accretion. You have accretion of low-angle aluminum material from the blast wave, and you also have accretion of aluminum-26 from either a blast wave or a Wolf-Rayet wave.
Yeah.
So how are those being modeled? I mean, it seems as though if it's numerical, like in the disk shrinking, then you have to be very careful about the processes that will, get matter from the high velocity flow onto the disk. And if it's the Wolf-Rayet wind, you weren't doing that hydrodynamically, so how was it being handled?
Yeah, the Wolf-Rayet wind is not doing hydrodynamically. The Wolf-Rayet wind is ad hoc, but the supernova impact is modeled hydrodynamically. So the tilting of the disk we take into account from the hydrodynamical calculations.
So Steve Desch has a model in which the aluminum-26 gets embedded in the disk on piggybacking in dust grains from
Yeah.
explosions. So
Yeah.
have you considered that type of transition from ejecta to disk?
Well, the problem that he faced was at that time the amount of iron in the disk was still comparable to the amount of aluminum in the disk. So he needed basically the supernova blast wave to inject all the material at the same time. And then he is faced by exactly the same problem, that the supernova doesn't cause enough accretion onto the disk. And I think the solution to that is to have the Wolf-Rayet wind produce the aluminum and have the supernova produce the iron. And then you have the discrepancy of a factor 1,000 between the aluminum enrichment and the iron enrichment at the same time. And whether or not you put it into dust grains or not, it's still not enough to explain the amount of aluminum in the disk. But you can explain the amount of iron in the disk this way. And that's also consistent with his conclusion.
So if you turn this machinery loose on another cluster that was young, like the Ryan Light cluster, would you predict the range of droplet disk sizes correctly? Or did you learn something from that?
I think you can learn something from that. And an experiment I've been doing is using the trapezium cluster as an example of which disk sizes are observed. And I started out with writing a code which, a lot of these processes are involved. And then I compared with the trapezium disk size distribution, and there was basically a perfect fit. And then I thought, well, this is too complicated. Why should I I don't want a complicated code to explain something. So I cut everything away, and the only thing that I left over was basically the dynamical encounters between the stars. And that still fitted the disk size distribution properly. So I think that even though here I advocate the supernova being responsible, at least in part, for truncating the disk, I think that the dynamical encounters are more important for the size distribution of the disks than the supernova itself.
Is that also a more compact cluster?
Yeah, that was a compact cluster. Yeah, that is a bit more compact than this, and it is comparable in the number of stars, maybe 1,500 stars or so.
You get a lot more encounters.
You get more encounters, yeah. And I can show you the picture. I have the picture actually. I can see if I can. I think I have it here, but it is. I don't want to give a second talk, but just to answer the question, I can show you this one picture. Well, let me show you the movie. That is maybe the most interesting one. So here, what you will see is basically how the size of the disk, the cumulative distribution of the disk size. So this is the size distribution of observed protoplanetary disks in the trapezium cluster. And these are different models. So this is the fraction of disks smaller than that size. And if in the calculation, the red line is the observed distribution, and the blue line converges to that blue distribution, and that's how you see happening here. So initially they were all big disks, and due to encounters, the disk size distribution sort of crawls to the observed size distribution. So in this case, I think you can explain the. I would say this is a plumber sphere, and this is a different density profile of the cluster. So this is the better movie.
So it must
So you see the
depend
cluster.
on how bound the cluster is. If it's
Yeah.
going to unbind rapidly, then you don't get
Then it doesn't work. Yeah, exactly. So this is gives a good fit. It doesn't mean that's the right solution, but at least it is a solution that could produce a size distribution of disks consistent with the observations.
This is only from 100 to 400 AU. There are no disks smaller than this?
They were not observed at that time. So the time I did this was the observational limit was about 100 AU.
But if you actually include the entire cluster, there will be way
There will be many more disks which are smaller.
So that will change
Yeah.
the amount, right?
Yeah.
So you need to produce those two.
Yeah. Okay. If you have no more questions, that's all.